The first topic for this week is going to be fundamental matrices. It's going to justify why it works as we said it works. So we're going to start by considering a linear ODE system, x prime equals p of x, with p potentially depending on time, and we want a solution on an interval for t between alpha and beta. In that interval, we have a fundamental set of solutions that is x1, x2, up to xn. So we are in the case of P being an n by n matrix, x being an n-dimensional vector, and we have n different fundamental solutions. Then we create the fundamental matrix. So this matrix psi is just, we write all the elements in our fundamental set of solutions column by column, one after the other. So this is a n by n matrix depending on time. The first column is one element of our fundamental set of solutions. The second column is a second element of our fundamental set of solutions, and so on. Notice how psi for t in the interval of existence of the solutions is not singular, because we have required x1, x2, down to xn, depending on time, to be linearly independent for every time. That means that all the columns of our matrix are linearly independent. That means that the determinant of our matrix is different than 0. That makes it non-singular. Non-singular means invertible. So any solution of our ODE system, x prime equal p times x, can be written as a sum of the fundamental sets of solutions. So we have x being the sum of a linear combination of our fundamental set, so constant times x1 plus constant times x2 times plus so on up to constant times xn. That means that we can rewrite this as the matrix psi multiplied by the vector c1, c2 down to cn. Because if that is how we are written, that means that c1 is multiplied by the first column of psi, c2 is multiplied by the second column of psi, and so on. So this is the right format to say that we can multiply a matrix n by n by a column vector c, and we retrieve a column vector x that is the solution of our ODE system. If we add initial conditions, so if we require our solution x to satisfy x at time t0 equal to a given vector x0, then we want to choose this vector c that we just introduced in such a way that that fixes it. So we want to choose c such as psi computed at t0 multiplied by c is equal to x0, our vector of initial conditions. Because psi is non-singular, that means it's invertible. That means that c can be written formally as psi at time c0 inverse multiplied by x0. That means that x, in general, can be written at psi at time t So x can be written as psi as the matrix psi multiplied by the inverse of psi computed at t0 multiplied by the vector of initial condition x0. We know that we can choose our fundamental sets of solutions in special ways. We have a lot of flexibility on how to choose these vectors. So if we decide to take them a bit special in such a way that they're satisfying that at time t0, all the elements except 1 are 0, and the one that is non-zero is the index, the ordering that we chose. So x1 will have 1, 0, 0, 0 at time t0. x2 computed at time c0 will be 0, 1, 0, 0, 0, and so on. If we have that situation, so we can also say that x index j at time t0 is equal to the element vector j, that is this vector of 0 everywhere except at index j, then we can define this matrix phi, in which we are writing, as for the fundamental matrix, column by column our set of fundamental solutions. What is the key difference between the two elements? Well, this new matrix that we have introduced is one fundamental matrix. It's a specific one that at time t0 corresponds to the identity. Because at time t0 we are putting one after the other our initial conditions, and our initial conditions form the identity. That means that if we have imposed an initial condition x0 at time t0, the inverse of psi at time 0 is the identity, so x is phi t times x0. We don't have to compute an inverse anymore. That means that phi t, the new matrix that we have introduced, is equal to psi t times psi inverse at t0. Let's make an example to make this a bit more clear. We have x prime equals the matrix 1, 2, 3, 4 times x. We can find the fundamental matrix, any fundamental matrix, and we want to find the fundamental matrix such that the fundamental matrix computed at 0 is equal to the identity. So let's start by just computing the determinant of this matrix. We work through it, and the eigenvalues of this matrix are -1 and 6. If we compute the eigenvector associated to this, we find that the eigenvector associated to -1 is 1 minus 1, or any multiple thereof. And the eigenvector associated to 6 is 2, 5. I'm going quite fast. We have seen these computations of eigenvalues and eigenvectors many times, but please, if you have questions about it, don't hesitate to ask about it in the discussion page. So a fundamental set of solutions is the match of these eigenvalues and the eigenvectors that we found. So 1 minus 1 exponential of minus t, and then the vector 2, 5 times exponential of 6t. We can put these two fundamental sets of solutions in a matrix. So we write this matrix psi, that is a fundamental matrix, one possibility in the infinitely many fundamental matrices, that is exponential of minus t, 2 exponential of 6t, and then in the second line is minus exponential of minus t, and 5 exponential of 6t. The general solution for this system means that we want c1 multiplied by the first fundamental solution, 1 minus 1 exponential of minus t, and c2 multiplied by second fundamental solution, that is 2, 5 exponential of 6t. We can choose c1 and c2 to solve for specific initial conditions. In particular, we want to solve for the initial conditions that will allow us to construct the special fundamental matrix that is valued as the identity at 0. So we want to solve for the initial conditions x0 equal x computed at 0 equal 1, 0, and x computed at 0 being 0, 1. These two are two different problems, so they have two different c1s and c2s that solve these problems. So we're going to go for it and try to compute them. First, let's go to compute c1 and c2 for x at 0 equal 1, 0. That means that, well, the exponential of minus t and the exponential of 6t disappear, are equal to 1. So we have c1 multiplied by 1 minus 1 plus c2 multiplied by 2, 5 equal 1, 0. This is a 2 by 2 linear system, so we can solve it very easily. The solutions, you can notice by the second equation, for example, that 5c is equal to c1. Then you solve this and you put it in the first equation, and you get that c2 is 1 over 7 and c1 is 5 over 7. So our first solution in this first solution that solves x at 0 equal 1, 0, we have that is 5 over 7 multiplied by the eigenvector that we found before, 1 minus 1, times exponential of minus t, plus the second block that is 1 over 7 multiplied by the second eigenvector that we have found, 2 over 5, exponential of 6t. The second solution is the one that satisfies initial conditions at 0, 0, 1. And we go through the same steps. We find C1 and C2, and we find a second solution. It has the same structure as before, but different coefficients. So we have the first eigenvector multiplied by minus 2 over 7 exponential of minus t, and the second eigenvector multiplied by 1 over 7 exponential of 6t. If we put this first solution and second solution together, each of them is a two-element vector. We might have written it more expanded, but it is always a two-element vector. So we can put one after the other in a column in a matrix. So our special matrix that satisfies that the fundamental matrix computed at 0 is equal to the eigenvalue, equal to the identity matrix, is this matrix here. I'm not going to read it out loud, but you see that exponential of minus t and exponential of 6 are scattered everywhere. And I'd like you to check that indeed, when you compute at 0, the two elements on the off diagonals, that means the bottom left and the top right, disappear, while the two elements in the diagonal give 1.